All right, so we've been talking about our theorems and postulates are written as if-then statements. And if-then statements are technically called conditional statements. Now, anytime you want to flip the if and the then part of a conditional statement, then the conditional statement is called a converse statement. So what we're going to focus on in this second half is we're going to take all of the postulates and theorems that we did in the first half. We're going to take all those if-then statements and talk about their converses. So one thing I initially want to tell you here is if you have a conditional statement and you flip it around and talk about its converse statement, that conditional statements and converse statements aren't always true statements. But in the case that we're going to talk about them, they will be. But I just wanted to throw it out here in this geometric example that we could say if a shape's a square, then it's a rectangle. That's a true statement because all the conditions that a shape needs to be called a rectangle, a square meets all those conditions. It has some extra conditions, but it meets all the conditions of being called a rectangle. So if we flip around the if and the then parts, and we said if a shape's a rectangle, then it's a square. Well, a rectangle doesn't have necessarily all the conditions of being called a square. So I'm going to say here that this isn't a false statement, but I would say that this statement is not necessarily always true, right? If a rectangle has four congruent sides, then yes, we may call that rectangle a square. But if a rectangle doesn't have all four sides congruent, well, then we can't call it a square. So the thing I just want you to know is converse statements aren't always true. I don't want you to think that they are always true, because that's what we're going to be really discussing today. All right, so this is what we talked about in the first half of this lecture, I guess you could say, is we had the corresponding angles postulate. And we started with the given information that if we have parallel lines, then our corresponding angles were congruent. So if we didn't have parallel lines, then we couldn't conclude that corresponding angles were congruent. So we always started with saying, if we have those parallel lines, and we went with that. We said, yes, let's have parallel lines. Then we could conclude that our corresponding angles were congruent. Well, now we're going to talk about this thing that's called the converse of the corresponding angles postulate. And what it's going to say is the exact reverse of what the corresponding angles postulate said. So the converse is going to say that if corresponding angles are congruent, then what must be true is that then we must have parallel lines in existence. So what we're going to show is if we can show that corresponding angles really are equal in a scenario that we have, then we must have parallel lines. And again, since this is a postulate, we're not going to have to prove or discuss the validity of this. This is foundational mathematical truth, that if our corresponding angles are equal, we're allowed to say that we must have parallel lines. So again, let's kind of compare these back to back here. We got corresponding angles postulate and the converse of the corresponding angles postulate. And what we could start off with as our given is now what we're going to prove in the converse of. And what we were asked to prove, basically, in the original is what we're going to be given in the other scenario. So just consider the given and the proof parts are getting flipped around when we talk about the converse of. So this is going to have a little bit different feel to it, but we're going to work through some of these proofs. So the converse of the alternate interior angles theorem, it says that if alternate interior angles are congruent, if they are equal, if you're told that, then what we can conclude is that we must have parallel lines. So in this picture, here's what we need to come up with. If alternate interior angles are congruent, so I need to see some alternate interior angles. So let's pick on these two angles right here. And we're saying that if these two angles are congruent, so I can mark them as congruent. And so there's my if. If I'm given that alternate interior angles are congruent, then what am I allowed to conclude? Well, what we're going to prove is that those two lines M and N, they must be parallel. So again, given that alternate interior angles are equal, we're going to prove, since this one's a theorem, that those lines must be parallel. And how are we going to prove this? We're going to use corresponding angles again, but it's going to have a little bit different feel compared to that first half video. So let's look at this proof. So given alternate interior angles are congruent, again, let's get that in our picture. So let's use, again, these two angles. Let's call these angles 1 and 2. Now, in the first half, the previous video, the connection between angles 1 and 2 was an incomplete connection because we knew angles 1 and 2 were alternate interior, but what we were trying to prove in the last video is that they were mathematically related, that they were equal. But this time it's different. We are told that these are mathematically related. They are equal. So here's what's going to be different is we can go ahead and connect angles 1 and 2 together. And this is our given information. So I'm going to go ahead and write this out. Angles 1 and 2 are equal. How do I know that's true? Because we're given that information. Now we still do need a third angle, and we're still going to use corresponding angles for now. So again, let's pick on angle 1 just because it's the first angle. Where is angle 1's corresponding angle? And it's down here. So there's angle 3. Now, what makes this different is angles 1 and 3 are corresponding angles, but can I say that angles 1 and 3 are congruent to each other? Well, I only know corresponding angles are congruent if the lines are parallel. And here's the issue. I don't know the lines are parallel in this problem. That's what I'm trying to prove is true. So there is my incomplete connection. Angles 1 and 3 are called corresponding, but I can't say that they're equal yet because I don't know the lines are parallel. Now you might say, but what about angles 2 and 3? Well, angles 2 and 3 are vertical, and vertical angles are always congruent, regardless if I have parallel lines or not. So I'll make a solid connection between them. And again, here's that circuit that I've created. All the angles are connected together. 1 is connected to 2, 2 is connected to 3, and 3 is connected to 1, just with an incomplete connection. So we need to talk about our two solid pieces of information in our proof. And here's the nice part, one of those solid things we've already talked about because it was given to us. So we get to go ahead and come over here and say, hey, let's put a little check mark between angles 1 and 2. That was given to us. Nice. Let's go talk about angles 2 and 3 now in our proof. So angle 2 is equal to angle 3 for the same reason it was in the first video, the vertical angles theorem. Check mark. And whenever we get two pieces of solid information back to back, whatever that middle angle was, that's the angle that's going to kind of bow out with substitution in our next step. So angle 2 instead of angle 3 is going to make an exit. So notice if angle 1 is equal to angle 2 and angle 2 is equal to angle 3, well, combining those two pieces of information, we can conclude that angle 1 must be equal to angle 3 by the substitution property of equality, or that's still the transitive property. So now that incomplete connection that we had before between angles 1 and 3, look what we just did. We just made it a solid connection. But we're not done with the proof yet because we were asked to prove that the lines were parallel. And we haven't gotten there yet, but we're one step away. So now here's what I want you to think about. That incomplete connection between angles 1 and 3, we just showed that it's a solid connection. We just showed that they're equal. So what we're saying here with that incomplete connection that is now complete is we just showed through substitution that these corresponding angles really are equal to each other. And if corresponding angles are equal, what are we allowed to conclude? We're allowed to conclude that if corresponding angles are equal, is that we have parallel lines in existence using the converse of the corresponding angles postulate. So now we can say we know M must be parallel to N by the converse of the corresponding angles postulate. And now we're done because we were asked to prove M is parallel to N, and we just did that. Now, a couple little things here. Any time in a proof that you are asked to prove that lines are parallel, the reason why the lines are parallel is always going to start with converse of. And it's going to be converse of whatever types of angles you just showed had a special mathematical relationship in the previous line. And for right now, it's typically going to be corresponding angles, but it's not always going to be corresponding angles, okay? But we're going to focus on corresponding angles for now. The other thing that I want to bring to your attention is that this proof, if you were to look at it backwards, is almost, I'm not going to say it's exactly like, but if you were to look at this thing backwards, if we started with parallel lines, then angles 1 and 3 were congruent corresponding angles, angles 2 and 3 were equal vertical angles, and we use substitution to show that angles 1 and 2, alternate interior angles, were congruent in that other proof. So theorem 3.1, if I go back here to the previous video, too far. If you were to look at this proof and the proof that we just did almost look like we just wrote it backwards, but it's not exactly the same, but it's pretty close. Now, I will say that these proofs, where you're asked to prove that lines are parallel, they're definitely going to have a little bit different vibe to them. And so again, you might have to practice with these before they make a little bit more sense. So let's look at one more together here, the same side interior angles theorem. And it says that if two lines are intersected by a transversal, but we're not saying those lines are parallel, we're just saying we got two lines, and we are told that same side interior angles are supplementary, then what we need to prove is that we really do have parallel lines. So if same side interior angles are supplementary, let's label some in our picture here. So I'm going to put them right here on the right side of the transversal. And so our given is going to be this. If angles 1 and 2 are supplementary, if we're told that that's true, then what we are going to prove is true is that those two lines M and N are going to end up being parallel. So again, if angles 1 and 2, if we're told that they really are supplementary, we're going to do some work to show that in the end, M must be parallel to N. And we're going to use the help of some corresponding angles to help us get there. So let's look at that proof. So again, let's go ahead and draw in over here. Let's talk about these same side interior angles. And our given information is we know there's a solid connection between them. We are told that those angles are supplementary. But here's where a baby step is going to come into play. Here's what technically we're given, is that angles 1 and 2 are supplementary. Nope. Given. Baby step now. What does it mean that those two angles are supplementary? Well, that means mathematically that angles 1 and 2 add up to be 180 degrees by the definition of supplementary or supplementary angles. So there's my check mark now. I knew that they had a mathematical relationship, but I needed to really define what that relationship was based on the vocabulary word that we were given. So now let's go find that third angle to help us out. And again, what type of angle is a really great angle to use? Corresponding angles. So angle 1's corresponding angle is down here below angle 2. And again, can I say that angles 1 and 3 are congruent corresponding angles? I cannot, because when are corresponding angles congruent? When the lines are parallel. But that's what we're trying to prove is true, is that we do have parallel lines. So instead of saying that these are congruent corresponding angles, there's the incomplete connection between 1 and 3. I need to show that corresponding angles are congruent, because if they are congruent, I've got parallel lines. Now, what's the special relationship between 2 and 3 is that they're going to add up to be 180 degrees by the straight angle postulate. So I know there's a solid mathematical relationship between them. So let's go talk about it now in our proof. Angle 2 plus angle 3 equals 180. and not because they're supplementary, but because of the straight angle postulate. And then check mark between angles 2 and 3. And again, notice now I've got those two pieces of back-to-back solid mathematical pieces of information in my proof. Now it's time for that middle angle, which in this case is angle 2, to bow out. But this one's going to have really the most different feel, because we're not going to get angle 2 to completely back out. So notice we're going to take these two pieces of information. If angle 1 plus angle 2 equals 180, and angle 2 plus angle 3 equals 180, what we're initially going to say is, well, both angle 1 and 2 and 3, they both equal the same amount, 180. Well, what that means is that angles 1 and 2, it's the same thing as angles 2 and 3, right? Because this is 180 and this is 180. So what property did we just use? Well, technically we use substitution, kind of a weird way substitution, or you could call that the transitive property. Now we got to use one more extra property here to get angle 2 to fully go away. Notice it's on both sides of the equation. So what property would we have to use to make it go away on both sides? Well, if we subtracted angle 2 on both sides, then angle 1 would be all by itself on the left side, and if we subtracted away angle 2 on the right side, angle 3 is going to be all by itself. So using the subtraction property of equality, that goes away. Now again, remember our incomplete connection was between angles 1 and 3, and we just showed through some substitution and the subtraction property that there is a mathematical relationship between those corresponding angles. So now, since these corresponding angles are equal, now we can say the lines must be parallel. And again, anytime that you're proving lines are parallel, the reason's always going to start off converse of, and it's going to be converse of what type of angles did we just talk about in the previous line? Corresponding angles, and then we get to throw in postulate. And we're done with that proof. This one's going to be the longest proof out of really all of the simpler theorems that we've been proving. Now, the converse of the alternate exterior angles theorem, it's going to be really, really the same thing, essentially, as the converse of the alternate interior angles theorem. So I'm not going to prove this one, but we'll talk about what it says here. What we're saying is, if we are given that alternate exterior angles are congruent, so if I marked those two angles as congruent, and I know that that's true because it's given to me, then what you can prove using some corresponding angles is that the lines must be parallel. So again, it's going to look exactly, purely exactly, just like the converse of the alternate interior angles theorem. What's the converse of the same side exterior angles theorem going to look like? The converse of the same side interior angles theorem that we just showed was true. So again, I could mark these two angles, 1 and 2, that are same side interior, and if I know that they're supplementary, then we can prove, with the assistance of some corresponding angles, is that we have parallel lines as well. So again, if you want to try those on your own, knock yourself out, that's good practice to try them. So I'm going to go ahead and stop there for this kind of second half. And then I'm going to do one more shorter video of a few examples that's really going to combine together these two videos.